Okay, so this is hopefully a nice explanation of the twin paradox in special relativity. What is the twin paradox in special relativity? Well, relativity says that there's no such thing as absolute velocity, it's all relative. It's a key point. All reference frames are equal. So here's the Earth here with two twins. One of the twins is going to stay on the Earth, and the other twin is going to go on a mission to a distant star 4 light years away. Then they're going to turn and they're going to come back, and then they're going to see how old each other are. That's it. So the one on the Earth, they think, I am stationary, and the other one is traveling away. So it's one of the results of special relativity is something called time dilation. Moving clocks run slow. So this clock's going tick-tock, tick-tock, but this one's going tick-tock, tick-tock, tick. So less time has passed for the moving twin. So when they get back together again, the moving twin is going to be younger than the one that stayed still on the Earth. But we know that velocity is just a relative concept. So from the point of view of the spaceship twin, they stand still. They say, I'm standing still. And the Earth moves off with some velocity, turns around and comes back again. So therefore, the spaceship twin says, my clock goes tick-tock, 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 and it's the Earth clock that goes tick-tock, tick-tock. So when they get together, the spaceship twin says, well, I was the one that was stationary. It was the Earth twin that was moving, so their clock is time dilated and slows down. Therefore, less time has passed for them. They're younger than me. So the paradox is, how can they meet up at the end and both agree? They must both agree because they're going to meet. So that's so the paradox is, from these two seemingly equivalent points of view, we're going to get different answers. Both think that the one that was moving, the other one, is younger. So how do we resolve this? So we're going to resolve this using space-time diagrams, because I like space-time diagrams, which is just x and t. Nothing too scary. We're going to plot the world lines, just the x, t coordinates of all the various spaceships and twins. We're going to use the result of time dilation. We're going to use the result of Lorentz contraction. And at some point, we're going to have to use Lorentz velocity transforms as well. So we're going to use 3 bits of mathematics: Lorentz time dilation, length contraction, and velocity transform. And then apart from that, we're going to draw lots of lines and some graph paper. We're going to go from 4 perspectives. Perspective number 1 is going to be from the inertial reference frame of the twin on Earth. We will draw the whole space-time diagram for that twin of everything that unfolds. We're going to look at the reference frame of the outward bound spaceship. We're going to look at the reference frame of the inward bound spaceship. Once we've done that, we can then look at the reference frame of the spaceship twin. And we'll see that, in fact, there is no paradox. They're both going to agree in the end that the traveling twin is the younger twin. But we can't just say that. Let's see if we can show it a bit nicer. So I'm going to try and go through this bit by bit by bit. So this is really, this is not just a case of doing the twin paradox. This is also a case of, this is a nice example of Einsteinian spacetime, Lorentz contraction, time dilation, velocity transforms, world lines. So this is like a massive revision of special relativity. Where's the camera? The camera's up there. I'll try and look at the camera as much as I can so that you can actually interact with this. And other than that, you will need, well, you don't need anything really, but I'm going to use graph paper and normal paper and a pen. So that's all I really need for this. So I want to draw the space-time diagram of the Earth twin. So what do I mean by that? I haven't got my ruler. Right, let's draw some axes. So I'm going to draw axes up the paper. And an axis across. It's just going to be one-dimensional. I'm just going to look at time and the x coordinate. That's all I'm going to do today. There's x, and this axis, so instead of just being time, I'm going to call it the speed of light times time. And 1 square, one unit of graph paper is going to equal 1 light year. So here we are at 0, 0. So here is the Earth. Oh, and I should say this is the initial reference frame of the Earth twin. So everything that we're going to do for the moment is from the point of view, or from the perspective, or from the relative, whatever, of the Earth twin. So what is the world line of the Earth? What space-time coordinates does the Earth have? Well, the Earth doesn't move, so x equals 0. That's where it is. So the space-time coordinates are just going to go straight up this line here. Excellent. We need to define something else then. So we need to define how far away the star is. The star is going to be 4 light years away. So let's mark this off. We've got 1 light year, 2 light years, 3 light years, 4 light years, 5 light years, 6 light years. So here is the star. So again, it's a proper length, so I'm going to call it L0 is equal to 4 light years. L0 equals 4 light years. So I can draw its world line. It doesn't move in the reference frame of the Earth. So its world line just goes straight up the page. So we've got the world line of the Earth, the world line of the star, and they're running in parallel because they have 0 velocity. So let's say that just at time equals 0, which is when the spaceship is just ready to leave the Earth. Think of it as a spaceship which is actually zooming towards the Earth. And just as it passes the Earth on the way to the star, that's when we both set our clocks to 0. So the spacecraft is traveling at 4/5 the speed of light. So v is going to equal 4/5 times the speed of light. And that means that I can represent this by a line on my space-time diagram with a slope 1 over beta, which is going to be 5/4 c. So I know that my spacecraft is at 0, 0, is at the Earth, time equals 0, x equals 0, and then it's got to some point hit the star. So when is it going to hit the star? So I've got a bunch of straight lines there. So I can write down the world line. World line for the outward bound spaceship. So CT is going to equal 5/4 c x plus 0. So that the spaceship coordinate at time equals 0 is x equals 0, it's at the Earth. So the star is at 4 light years. So at what time am I going to get to 5/4 c times 4 light years? So CT is going to equal 5c. Or time is going to equal 5 years. Okay, so now I know some coordinates. I know that the coordinate for my outward bound spaceship, first coordinate is here, because it's at the Earth, and the second coordinate is at t equals, I haven't written t, have I? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 is at x equals 4 and ct equals 5. So I can draw a straight line. So that is the world line of the outward bound spaceship. It is zooming up to the Earth, passes the Earth, and both of them reset their clocks to t equals 0. Then it zooms away, and eventually it's going to reach the star at x equals 4 light years at a time ct equals 5 years. So that's the outward bound trip. For the return trip, we can draw the world line for the return trip as well. So that's just going to be symmetric in this case. So it's taken 5 years for the outward bound trip. So it's going to take 5 years for the return trip, assuming that the turnaround is instantaneous. So I can draw the world line of the returning ship like this. So I'm going to go out this way, back this way, and then we're going to meet up with the Earth at ct equals 11. So I've already worked out how old the earthbound twin is going to be. It has taken 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 years have passed on Earth between the spaceship leaving and the returning ship coming back. So it's taken 10 years. How long does it take on the spaceships? So we need to break this down into two parts. We need to look at the time on the ship on the outward bound and then the time on the ship on the inward bound. So this is going to be Lorentz time dilation. So let's just consider the time for, let's just call it a tick-tock. The time between tick-tocks on the Earth's clock. This is all as viewed by Earth equals 1 year. Because it's in the same reference frame as the clock. So that in that case, it's proper time. So what do we see for the time for one tick-tock of the outward bound, the outbound clock? So that is a moving clock. So we're going to perceive that clock to run slow. So this is time dilation. So what do we have? Delta t naught of proper time times a factor gamma is equal to delta t. So here gamma is equal to 1 over the square root of 1 minus v squared over c squared. So it's independent of direction. So how much time passes on Earth for one proper tick-tock on the spaceship? So in the spaceship, they have their clock. And they're looking at their clock. It's going to tick-tock 1 year. And what I want to know is, on Earth, I'll start my clock at the same time. So they're going to stop their clock. After 1 year, I'll stop my clock as well at that time. They're going to look at mine. How long has passed from me for them, for the spaceship to register 1 year? So we need to know what this gamma factor is. So if I was to put in 4/5 c for the velocity, gamma will come out to be 5 over 3, 5/3. So delta t naught is equal to 1 light year, 1 year. Gamma is equal to 5/3. So therefore delta t, the time that passes on Earth, is 5/3 of a year. Or what's that? 5/3. 1.66. 1.66 recurring years. So their clock, according to Earth, runs slow. At 1.6 on Earth, 1 year passes in the spaceship. So we can mark that onto our diagram now. How do we do that? So really, it's a recalibration of this scale. So I'm going to draw another scale. So after 1.66 years, 1 year has passed on the spaceship. Why on earth didn't I bring my calculator? Because now I just do it for all the other ones. So we can mark off how long is 2 years going to be. And that's going to be about here, 2 years. I suppose I could just do it like this. 1.6 plus another 1.6 plus another 1.6 gets me to 5, plus another 1.66, plus another 1.66, plus another 1.66 gets me to 10. So here is the time as seen on the spaceship. 1 year, 2 years, 3 years, 4 years, 5 years, 6 years. So just at that point, and that point, so that's 1 year on the spaceship clock, 2 years in the spaceship clock, 3 years in the spaceship clock. So that's what the spaceship clock will read: 1 year, 2 years, 3 years. As observed, always in this case by Earth. So when they reach the star, Earth says 5 years have passed. And Earth says 3 years have passed for the spaceship. So we can do the same on the way back, because on the way back we have the same time dilation because it's the same velocity. The same speed, sorry. So again, we're going to have another tick-tock here, another tick-tock there, and the last one here. So it's going to be 1, 2, 3, and then 4, if I done that one right, 5, 6. 1, 2, 3, 4, 5, 6. So 6 years in total have passed for the twin on the spaceship. So, my friends, we can write this all down. So the time on Earth equals 10 years. So the time out equals 3 years. Time, oops, can't write time, back equals 3 years. So 6 years for the spaceship twin. So the spaceship twin is younger. Hurrah. Just by drawing a very nice little space-time diagram. Spaceship twin is younger. Fine. So we should be able to turn this all around now from the point of view of the spaceship twin. And naively you think, well, I'm going to get exactly the same result. The Earth's going to be zooming away and then the Earth is going to be zooming back. So I should be able to draw something very similar to this. But instead of the spaceship going this way, this is going to be the spaceship and the Earth's going to be going that way. And it's going to join up again. So before we can do it for the spaceship twin, we're going to do it from the point of view of the outward bound ship. Then we're going to do it from the point of view of the inward bound ship, and only at that point will we combine these two to look at the path of the spaceship twin. Right. I get completely confused. So we need another bit of graph paper. Spaceship twin. Outward bound spaceship twin. Outward bound spaceship twin. So I'm going to draw my axis slightly off center because I need more room on one side than the other side. So let's draw, what do I need? Let's draw it here. So I'm going to have time axis again going up the paper. And they're going to have a space axis going horizontally. So So again, I've got x in this direction and CT going up the page. I hope you can actually see all this. Otherwise, it's a bit useless. Okay, so this is from the initial reference frame of the outward bound ship. Everything we're going to do is from the initial reference frame of the outward bound ship now. So at time equals 0, they are on the Earth, so the Earth must also be at x equals 0. Then the Earth's going to move off with velocity minus 4/5 c. So we can write down some of the things that we know, including that. So what do we know about this twin? The ship now. The ship. What is the distance to the star? Well, it's going to be a distance L, which is L naught over gamma. The distance to the star is going to be Lorentz contracted. So in the Earth reference frame, the distance to the star was 4 light years. That was a proper time. Those objects were not moving in the reference frame of the Earth. But now we're in the reference frame of the outward bound ship, so they must be moving. So they're going to be Lorentz contracted by a factor L naught over gamma. Which is going to be, so therefore the distance between the spaceship and the star is going to be 12/5, if you work it out, so that's 2.4 light years. HT years. So the distance we have to travel is less. It's Lorentz contracted. Excellent. What else do we know? The velocity of the Earth. The velocity of the Earth is going to equal minus v, which is minus 4/5 c. The velocity of the star is going to equal minus v as well, minus 4/5 c. Excellent, which means we can start to draw world lines now. Because all we need to know for world lines is the velocity and one point in time and space. It's just a straight line. So we can define it all by knowing m and knowing the constant c. So what about this velocity of the inbound, the inward ship? Because we're going to have to draw that in our graph. What velocity does it have? Well, that's a good question now. So we know the velocity from the reference frame of the Earth. So now we need to work out what velocity would the outward bound ship see of the inward bound ship. So that's not quite so obvious that we can simply say that it's 2 times v. Let's say that the velocity of the ship was close to the speed of light. I mean, 4/5 is actually quite close, isn't it? So let's say it is 4/5 c. Then we've got the ship going out. We've got the star, so the star is moving at 4/5 c according to the ship. We've also got the inbound ship moving at 4/5 c. According to the Earth, it's moving at 4/5 c, 4/5 c. So we've got 4/5 c for the outbound ship, 4/5 c for the inbound ship. So naively, we would just add up those two velocities and say the velocity this one sees is this one with a closing speed of 8/5 c. 8/5 c is bigger than c. And we're not allowed to have anything bigger than c. So that's not going to work. So we're going to have to use Lorentz velocity transforms to work this out. But it's relatively straightforward. So we just need a couple of reference frames. So here's the Earth. These are things that we know. And here is the reference frame of the outship, traveling at velocity big V. And here is the reference frame of the in-ship, and it is traveling at velocity minus v. Lorentz velocity transforms, what are they? So we write them as Vx dash equals Vx minus V over 1 minus V over c squared Vx. So we just need to define all these terms. So Vx dash is going to be the velocity of the inbound of the in-ship as seen by the out-ship. So we know it's got a velocity minus v as measured by Earth. And all we need to know is what velocities it have as measured by the outward ship. V of x is the velocity of the inbound ship according to Earth. And big V is the velocity of this one, of the outbound ship. So we can plug all those in. What's it going to equal? So Vx dash is going to equal minus V over 1 minus V over c squared minus V, which is equal to minus 40 over 41c, which is less than the speed of light, but still faster than 4/5 c. Just for completeness, let's work out gamma. So gamma for 40/41th of the speed of light is quite big, 4.55. This term gamma that crops up in special relativity is now going to be 4.55. Right. So let's ask the question. When does the handover occur? When do the two spaceships cross? So we probably just about have enough to do this. Ugh. So we need the world line of the star. When the star crosses the world line of the outward bound spaceship, that's when the twin is going to transfer from the outward bound to the inward bound. So we have a world line. Ct is equal to 1 over beta x plus some offset d. It's just a straight line because it's going at constant velocity. So we know for the star, beta is equal to minus 4/5 c. That is its speed. And we know that at t equals 0, the star must be at coordinate x is equal to plus 2.4. That's its starting point. It starts at 2.4 light years distance. That was the Lorentz contracted distance between the Earth and the star, or between the outward bound spaceship when it starts and the star. Which means I can work out, I'll let you work this out, the world line is going to be Ct minus 5/4 x plus 3. So that is the world line for the star. So now we can ask the question, when does the star get to the outward bound ship? I'll go back to the space-time diagram. This is the world, so going straight up here, this is the world line of the outward bound ship. I suppose I could mark this on now. 1, 2, 3, minus 1, minus 2, minus 3. We're going to need a lot of these. Minus 4, minus 5, minus 6. Minus 7, minus 8, minus 9, minus 10, minus 11, minus 12, minus 13, minus 14, minus 15. How many do I need? It should do. And we might as well do the time axis as well as we're here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. All right, so we've got our axis marked off. So the star is at 2.4. And the Earth begins here. So we've got the starting points for the star and the Earth. So when does the star, at traveling at some velocities, going up here, is going to cross this axis. It's going to cross the world line of the outward bound ship. When does that happen? So that's going to happen at x equals 0. So CT equals 3. Nice and easy. So we can mark this on. CT equals 3. So now I've got 2 points on my world line, so I can draw the world line of the star. Just for completeness, I'll just draw it extended. So there is the world line for the star. So from the point of view of the outward bound ship, the star is 2.4 light years away. And after 3 tick-tocks of the outward bound ship, the star has reached the ship. 3 light years, 3 years have passed on the ship. Which, if you look back at this one, this is from the point of view of the Earth. How much time passed on the ship? 1, 2, 3 years. Excellent. Right. So now we just need to draw the world line of the Earth and the world line of the inward bound ship. So the world line of the Earth is very straightforward because it's going at 4/5 c. So I can draw that on here. So after 5 years, it's gone 4 light years. Is that right? After 5 years, after 4 years, it has gone. Yes, that's right. After 5 years, it's gone 4 light years. So the world line of the Earth. Going to draw it pretty long. So there is the world line of the Earth, and it should be parallel to the world line of the star, because the relative velocity between those two is 0. So the distance between those should be constant. It's always going to be 2.4, hopefully all the way up here. So there's the world line for the Earth. So all we need to do now is draw in the world line for the inward bound spaceship. So we know its velocity. Its velocity is minus 40/41ths of the speed of light. And we also know a coordinate. I know that at x equals 0, at x equals 0, it must cross the axis at CT equals 3. It must be flying in, crossing here, and it's going to go up here, and it's going to eventually connect. So what is the world line of the inward bound, the inward ship? CT is again equal to 1 over beta x plus some constant. So I know what the velocity is. It is minus 41 over 40x plus some constant. And at x equals 0, CT has got to equal 3. So therefore the constant E equals 3. So the world line is CT minus 40 over x plus 3. This is for the inbound ship. I suppose the last one we need to write down is the world line of the Earth, which we've already drawn. So the world line of the Earth. So that's just CT is equal to minus 4/5. 5/4 x. With no constant, because at t equals 0, it's at x equals 0. So that's the Earth. So what we want to know is, when does the inbound ship and the Earth, where do these meet? Because that's going to be when the spaceship twin arrives back at Earth, when the inbound ship matches the coordinates of the Earth. Well, we've just got 2 lines. We can handle 2 lines, can't we? Of course we can. When do they meet? So we need minus 41 over 40x plus 3 to equal minus 5/4 x, in which case x is going to equal minus 13.33 repeating. And then you can work out the CT coordinate, and it's going to equal plus 16.6 repeating. That's when the inbound meets the Earth. So we can draw this now on the space-time diagram. So what was that? X is equal to minus 13.3. So what do we got? All the way down at the bottom, minus 13.3. This is really not very good. Let's zoom out so you can actually see what I'm doing. Minus 13.3. All the way up here. Dun, 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 dun. And hopefully this has got coordinate 16.6. That's pretty good. So the coordinate here is minus 13.3 repeating, 16.6 repeating. So at that point there, that is where the spaceship, the inward bound spaceship, and the Earth meet. So I got 2 points now for the inward bound world line. It must be here at time 3 years. Just as the star passes the outward bound ship, so the inward bound ship must also be at that position to hand over. And then I know that at this time up here it meets the Earth. So I can draw the world line for the, I've only had a blue pen, for the inward bound ship. There we go. So there's the world line for the inward bound ship. It's catching up with the Earth, it's catching up, and it catches it just at this time. So now we need to think about all the different times and all the different ships. We now have a space-time diagram. Perfect. So we need to think about the time on the Earth, the time on the outward bound ship, and the time on the inward bound ship. So the time on the outward bound ship is very straightforward because that's the one that we are in. So there's 1 year, 2 years, 3 years. 3 years have passed on the outward bound ship before it meets both the star and the inward bound ship, all at the same time. 3 years have passed on the ship. What about on the Earth? So now we're back into the realms of time dilation. So 1 year on the outbound ship really just equals 1 year on the outbound ship. Okay, that's kind of obvious because that's the clock at rest, because that's your clock in the outbound ship. 1 year on Earth. So Earth measures a proper time, 1 year. How much time did we measure for that? Well, times gamma, which is at 4/5 c, it's going to equal 5/3 years. So it's the same as the Earth measured for our clock slowing down, which is the reverse situation. So now we're going to measure the Earth clock slowing down by the same amount, 5/3. So we can mark that onto our timeline. So 5/3, 1.66 repeating. So after 1.66 years, according to the outward bound ship, the Earth clock have reached 1 year. And I just need to do this all the way up. If I was better at this, I would say here's one I did earlier, but 1.66. So let's do 1.66 is about there. And about there. So that's them all marked. So 1 year, 2 years, 3 years, 4 years, 5 years, 6 years, 7 years, 8 years, 9 years, 10 years. So we can mark can now mark where that occurs. So after 1 year, so the clock on Earth at this point will read, at this point will read 1 year. Move this one along, so there's 2 years, 3 years, 4 years, 5 years, 6 years. Seems a big jump. 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So according to the outward bound ship, the Earth's clocks will read 1, 2, 3, 4, 5, 6, 7, 8. Will read 10 years when the inward bound ship catches up. 10 years have passed, exactly as Earth also measures. So for the twin on the ship, 1, 2, 3 years have passed. There's a changeover. I wonder what the Earth makes of this. So the Earth reckons that this changeover happens here, which is in fact 1.8 years. So at the changeover, the Earth measures 1.8 years, and the outward bound ship measures 3 years, which is just time dilation. So now we need to think about, what about for the inbound ship? How many years pass for this inbound ship? We got, so the twins age 3 years here, the shipborne twins were age 3 years. The shipborne twins still got to go all the way here to get to the Earth. How much time has passed for the twin? So it's just the same thing. We need to do a bit of time dilation. Except now we've got a different velocity. So 1 year on the in ship. So 1 year on the in ship times gamma. Now it's 40/41th c is going to equal 4.55 years on the outbound ship. So when our clocks on the outbound ship have gone forward 4.5 years, only 1 year is going to have passed for the inbound ship because it's traveling so fast. It suffers tremendous time dilation. It's going at 40/41th of the speed of light, whereas the Earth's only going at 4/5 the speed of light. It's only getting at 80%. It's dawdling. So we need another axis here. So let's start it. All I need to do is mark off 4.55 years. I'll do it in red again. 4.55 from where, so I'm going to start the clock just as it passes. So 0 is 1, 4.55 from there. It's going to get me to here. And 4.55 from there is, going to get me to here. So let's call this 0. So this is the time on the inbound ship. Let's just say, let's just define this as they're going to see 0. 1 year has passed for them, 2 years have passed for them, 3 years have passed for them. So in 4.5 years for us, only 1 year has passed for them. So we can mark this on. So 1 year has passed here, 2 years has passed here, and 3 years has passed here. So 1 year has passed, 2 years have passed, 3 years have passed. So how much time has passed for the twin? 1, 2, 3, 4, 5, 6. 6 years. So for the reference frame of the outbound ship, 10 years have passed for the Earth, 6 years have passed for the twin, for the spaceship twin. So again, that's the same thing. So let's just write that down. So this has all been from the initial reference frame of the outbound twin, of the out twin, or the out ship, whatever you want to call it. So the time on Earth equals 10 years. The outward trip, they measure as 3 years. Time between starting and the star getting to us. And the in trip also takes 3 years. So in total, that's going to be 6 years. So the ship, twin, is younger than the Earth twin. So from that point of view, they all agree. So the penultimate one we need to look at now is from the point of view of the inward bound twin. So we just need to draw the space-time diagram of the inward bound twin. So you might naively think all you need to do is take this and turn it around. But space-time doesn't quite work like that. So what we need is axes, a cheat sheet, get rid of all this, some new graph paper. So this is going to be the initial reference frame of the inward ship. So I need my large axes again. Let's do down to 18. Let's do across. Dun, dun, dun. So the same axes, X, and up here, C, T, time. So I can label them again. 1 year, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 years for the inbound twin. And I can label the other axes. 1 light year, 2 light years, or -1, -2, -3, -4, -5, -6, -7, -8, -9, -10, -11, -12, -13, -14, -15. All right, so there is the space-time for the inward bound twin. So let's write down all the various things that we know about the situation, because we know quite a lot. Because all we have to do is draw the world line of the inward bound twin. That's easy, that's just straight up here, because they don't move in their own reference frame. And we just need to draw the world line of the Earth and the world line of the outward bound twin. Do the time dilation as we've done before, add them up, and then we're done. It's slightly more, it's only slightly more awkward, this one, but it is slightly more awkward. So what do we know? We know that the velocity of the Earth is going to be +4, fifth c. We know that the velocity of the out ship is going to be plus 40/41 c. So you should make sure you're convinced of that, either through symmetry or through doing all the rounds, coordinate transforms if you wish. So the outward bound ship is going to be 40/41 c. It is going quite quickly. What else do we know? So at t equals 0, the x-coordinate of the Earth must equal the x-coordinate of the out ship. Because at t equals 0, that's when the whole thing starts, and the out ship is at the Earth. The twin is just boarded, well, the ship's flying past, and the twin jumps onto it. What else do we know? So we know that when the out ship reaches the in, so at that point in time, when the out ship reaches the in ship, that distance to the Earth must be 2.4 light years. So the distance between that coordinate and the Earth must just be L0 over gamma, which is 2.4 light years. So, given these constraints, you can now work out two straight lines. We know the slopes, and we know that at t equals 0, the x positions, we don't know what the x positions are, but they must be the same. And we know that when the outward bound ship reaches the inward bound ship, so x equals 0, just at that point, the Earth must be 2.4 light years away. So its x coordinate must be 2.4 light years. So therefore you can work out, so the world line for the Earth is CT equals, so it's 5/4 x plus 16.6 repeating. And the world line for the outbound, for the outship, CT is equal to 41/40 plus 13.6 repeating. And at t equals 0, at the beginning of this whole thing, what does the coordinate x Earth equals x ship? Oops, this is the out ship. And that equals minus 13.3 repeating light years. Right, I know enough to plot some graphs now. They're going to both start at minus 13.3 distance away at t equals 0. One of them is going to cross the axis at my axis of the inward bound ship at 13.6 at time ct equals 13.6, and the other one's going to cross at time ct is equal to 16.6. I mean, if you know the, you could do it all with angles if you wanted to in a protractor, but I just like doing it with 2 points. So 13.3, let's mark that on. So this is the initial coordinate of the Earth and the out ship. Now at 13.3, time is equal to 13.3. That is when the out ship makes it to the in ship. This is the world line of the in ship. This is going to be the world line of the out ship. And at 16.6, that's when the Earth is going to cross. So let's draw those two world lines. Here's the world line of the outward bound spaceship. And here is the world line of the Earth. So they're both traveling towards the inward bound ship. So that's when the changeover is going to happen. So that's when the outward bound ship matches with the inward bound ship, and that's when the twins are going to jump ships, and then eventually we're going to meet up with the Earth. So the first bit to do is how much time passes for the twin on the inward bound ship. So it's 13.3, so let's call that 0. So 13.3, 14.3, 15.3, 16.3. I've drawn that slightly wrong. It should be 13.6. Whoops. Oh, it should be 13.6. I've drawn it very slightly wrong. Anyway, so the time between here and here is going to be 3 years. 16.6 minus 13.6 is 3. 3 years pass between the twin boarding the inward bound ship and the inward bound ship hitting the Earth. So what happens before that? I need to know what's happening to the twin here and what's happening to the twin that stays on Earth. So again, we just need to mark this now in units for the two different speeds, two different reference frames. So we have to do some time dilation again. I mean, you can just look back at the other results, and by symmetry you can work it out. So 1 year, on Earth equals what? Well, it's going to be 1 times gamma for 4/5 the speed of light, which is going to be 1.6 repeating years on the in-ship. So for every 1.6 years on the inward bound ship, 1 year passes for the Earth. So we have to mark this on now. So the first one we can do is at 1.6. 1 year has passed for the Earth. So I need to do this all the way up. Adding on my 1.6s. Well, it's really more like 1.7, isn't it? 1.66. Another one there. One at 5. Here. Another one here. Another one at 10. It's going to be a mess. Anyway, here. 1.6. Here. Another 1.6. Here. And lastly, another 1.6 here. So these are all. So 1 year passes on the Earth, 2 years, 3 years, 4 years, 5 years, 6 years, 7 years, 8 years, 9 years, 10 years. Aha, you're thinking. So let's mark this on. Earth. 1 year passes on the Earth. 2 years passes on the Earth. 3 years have passed. 4 years have passed. 5 years have passed. 6 years. 7 years. 8 years. 9 years. 10 years. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we agree. For the whole round trip, 10 years pass for the Earth, which is exactly the same as the Earth thinks, and is exactly the same as the outward bound ship thinks. For the whole experiment, 10 years passes for the Earth. Hurrah. What about how much time passes on the outward bound ship now, between it starting its journey and getting to us? So we've got 3 years between here and here. How much time passes on the outward bound ship between here and here? So again, it's time dilation. So 1 year on the out ship. So we've got 1 times gamma of 40/41ths C is going to equal 4.55 repeating years. 4.55 years passes on the inward bound ship for 1 year to pass on the outbound ship. So it's symmetric with what we saw for the previous case. 4.55. So there is 1 year for the outward bound ship. 4.55 plus 4.55 is about 9. 2 years have passed. And 4.55 plus that is going to equal, way up here, 3 years have passed. So mark it there, mark it here and here. So clocks are going to read 1 year, 2 years, and eventually 3 years. Clocks have slowed down dramatically. This is going fast. The outward bound ship is going at 40-41 the speed of light, which means that the slope gets dragged further and further down. The faster you go, the closer you get to going at 45 degrees. 45 degrees is the speed of light. And time slows down. And it goes as gamma. So there might only be a relatively small increase in speed. Time slows down a lot. 1 year passes. It takes 4.5 years for 1 year on the outward bound ship to pass. So only 3 years have passed on the outward bound ship. And then we've got another 1, 2, 3, because they go at 1 year a year. So we've got 1, 2, 3, 4, 5, 6, 6 years in total. So this is the initial reference frame of the, what was that? The in-ship. So what did they measure? The time on Earth equals 10 years. They measured the time on the outship equals 3 years. And they measured the time on the in-ship equals 3 years. The time for the twin is 6 years. So the ship twin is younger. Excellent. So in those 3 initial reference frames of those 3 perspectives from the Earth, the outward bound ship and the inward bound ship, all 3 agree it takes 10 years for the whole thing, for the Earth, and it takes 6 years if you add up the time experienced on the outward ship and the inward ship and the outward ship and the inward ship. So they all agree it takes 6 years. So what about, right, before we do that, let's have a look. So we'll go back to this one for the inward ship that we were just playing with. So here's the handover. This is where the twin jumps. The twin is on the outward bound ship, and then he jumps across to the inward bound ship. So what time does the Earth think this occurs? Well, at that point, the Earth's clocks read 8.2 years. Interesting. So, new piece of paper, because this is where it becomes not a paradox. So now we're going to do it from the point of view of the space twin, of the ship twin. So, from the point of view of the ship twin, it's not an inertial reference frame because we're going to use 2 of them. One, we're going to do something. We're going to start. So there's going to be leave the Earth. So let's glance at Earth's clock. It reads T Earth equals 0. Let's glance at the out clock. It's going to read T out equals 0. Two, we're going to arrive at the star. I've nearly completely forgotten about the star, which is the same as meeting the in-ship. So we're just going to arrive. So let's glance at the Earth's clock. So T Earth. What time does the Earth think this occurs? We worked it out somewhere. There it is. So here is the inertial reference frame of the outward bound ship. Outward bound ship, outward bound ship, outward bound ship, and then at 3 years, the star has caught up with us. We've collided with the star. Or that we could say that at the same point, the inward bound ship crosses us. And we glance across, and the Earth thinks that 1.8 years have passed. Time dilation. We measure 3 years, they measure less. They measure 1.8 years. 1.8 years. So, glance at, I'm going to change this. It's not the out clock, this is the twins clock. Space the ship twin. Their own personal clock. So we're going to glance at the ship twins clock. So that should be twin. T twin is going to equal 3 years. One year passes for the ship twin, 2 year passes for the ship twin, 3 years passes for the ship twin. Glance across, 1.8 years has passed on the Earth. Fantastic. Now we change reference frames. 3. We're just going to leave the star on the in-ship. What are we going to do? We're going to glance at the Earth's clock. Well, let's do it. Here we go. This is the inertial reference frame for the in-ship. Here we are. This is the crossing point. This is where the in-ship crosses the out-ship. So that's where the handover takes place. We glance across at the Earth. So the twins clock reads 3 years. The Earth clock reads 8.2 years. We glance at our clock, at the ship twin clock, our own personal clock that we're carrying with us, and that is going to equal 3 years. Because we instantaneously jump from the out-ship to the in-ship. No time passes for us. 3 years. Excellent. And then lastly, for the in-ship passes Earth, or arrives back at Earth. So we're going to glance at the Earth clock. And that's going to equal 10 years. And we're going to glance at the ship twin clock, at our clock. And that's 3 years, plus it takes 3 years to get there, so that's going to be 6 years. Our clock goes 1, 2, 3, 4, 5, 6. Whereas the Earth goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how do we reconcile this? It costs time to change reference frame. So here we go. 3 years, 3 years. For the twin on the ship, it doesn't cost any time to change reference frame because we're being a bit silly and we're assuming that we can change reference frame instantaneously. But that's fine. But from the point of view of the Earth, it takes ages for us to change reference frame. Highlighter time. 1.8 years, 8.2 years. the Earth's clocks wind on by whatever the difference between those two things is, 7 and a bit years. 6 and a bit years. It takes a long time for that transition to occur. So that's why it is not a paradox. It's not a paradox because one of the twins changes reference frame, which is another way of saying one of the twins must experience a non-inertial reference frame. They must feel a force. The twin and the Earth just presumably hanging around in a space station, say, and they're in a beautiful inertial reference frame, and they sit in that reference frame for the whole trip. Here they are. Inertial reference frame of the Earth twin. They sit in their inertial reference frame, nothing happens, and then they stop the clocks. So they're in the same inertial reference frame for the whole trip. Whereas the spaceship twin, it's first of all in one inertial reference frame, and then they have to switch to a second inertial reference frame. So at that point here, they change inertial reference frame, which much in real life, in real life, they must decelerate and then accelerate, because they need to change the velocity. So you could do this all with infinitesimally small slowing down steps and solve it for many, many, many inertial reference frames, and you'll get the same answer. It'll look a bit more elegant and it wouldn't be instantaneous, and then you would get rid of the instantaneous nature of it. So as they come up here, as they do their slowing down, this takes ages, and then they speed up again, and then they meet. So it's this turnaround that is the problem, which is why it is not a paradox, because the turnaround takes a long, long time. So hopefully that's at least walked you through some of the ideas of the twin paradox. So what have we done? We've met space-time diagrams. We've met world lines. We have looked at time dilation. We've looked at Lorentz contraction and Lorentz velocity transform. So we've used all these relatively simple tools of special relativity, applied them to this problem to show that, in fact, from all the different perspectives, everything works out. Everybody agrees that the ship twin is younger, in this case, by 4 years. I hope that's helped. Thank you very much.